So I guess we can start. I was David Mitchell, who prepared this version of the notes, and he was worried because the lectures were prepared for 75-minute classes, and same as the lectures I used to teach at Notre Dame, they were usually given in 75-minute classes. So he was concerned whether we'd squeeze them in an hour or not. We got through the first one, but I suspect some of the others might run a little long. We'll see. So now we're going to, so the bit flipping is not really belief propagation. It's just a hard decision, iterative message passing algorithm, just to give you an idea of how these things work. Belief propagation is a soft decision algorithm. The messages that are passed are probabilities, which represent a level of belief about the value of the code word bits. Otherwise, what's the current probability that this bit is a 1 or a 0? Okay. And this is carried out, the decoding can be carried out in the probability domain or the log domain. It's more convenient to work in the log domain. It's kind of the similar thing with the Viterbi algorithm and BCGR and things like that, in that you wind up eliminating multiplications and doing additions if you work in the log domain, which is easier in terms of implementation. Actually, I mean the description here is in the log domain. I think it's easier to understand what's going on in the probability domain. But you'll see, if you've never seen this before, it gets a little, one part of it gets a little complex. We won't go into all the details. And the other reason, it's not only that they are more complex to implement multiplications in hardware, but if you have products of probabilities, you can run into numerical stability issues also. So the log domain algorithm is also referred to as the sum product algorithm when you operate in the log. There's lots of different terminologies for these iterative decoding algorithms. So we start with the log. Now here's where we get into the handwriting. So you might want to check, whenever you see the handwriting here, check your page, and if it's not clear, you might want to make a note. And some of these that were written in weren't, they're a little hard too. I'll try to point that out. So the log likelihood ratio of a binary random variable is just, it's the ratio of the probability that's equal to 0 divided by the probability that's equal to 1, and the log of that. And of course, these two guys have to add up to 1. So we can write it this way if we want. If the probability that bit's 0 is greater than the probability that's a 1, then that means that this is greater than 1 and the likelihood ratio is positive. And the larger the difference is, the bigger the positive value is. And similarly, if the 1 is more probable than a 0, then the likelihood ratio is a negative, and the more likely 1 is, the larger negative value we get in the log likelihood ratio. So the sign of the log likelihood ratio, if you want to think of it this way, if you wanted to make hard decisions based on the log likelihood ratio, you would just take the sign. Because whenever 0 is more likely than 1, you have a positive LLR, which means you'd estimate a 0. And if a 1 is more likely than a 0, you're going to estimate a 1. So hard decisions can be made from the signs. And the magnitude determines the reliability. The higher the reliability, like we said, the bigger the difference is between these two probabilities, the larger the LLR is. That means that estimate that you would make would be more reliable. If you have LLRs close to 0, it means the reliability of those bits is not very great. Okay, there was something else I wanted to mention. Well, okay, one thing we should keep in mind here, I think in this part of this lecture, we're going to be we're basically going to be dealing with the Gaussian channel, where we're assuming that the received symbol goes through a matched filter and is sampled, and a real number comes out. Okay, and we'll see that a little bit more later. So this algorithm takes as inputs a priori probabilities on the code bits. So these are just if we get a likelihood value, or we get a value off the channel, we can convert that into a log likelihood ratio corresponding to that bit. And that would be a so-called a priori probability, meaning before we start decoding. This is the likelihood of this bit. We also know the H matrix, the code that we have, and we have some maximum number of iterations that we're willing to do. The output is a posteriori probabilities on the code bits. Otherwise, after we go through iterations, we have now probabilities or log likelihood ratios on each bit that are after taking into account the received information and the code constraints. And then the goal is to make a map probability decision for each code word bit. That's the goal. Of course, this algorithm is not a map algorithm. It is in one particular case, which can never happen. I think it's in the notes here, so I'll wait to mention that. So each variable node sends a message. We refer to as extrinsic information to each check node it's connected to, very much like what we've seen. Extrinsic, what do we mean? It doesn't pass information to the receiving node that the receiving node already possesses. Otherwise, this variable node presumably got information from that check node on the previous iteration. So what it received from that check node is removed. This, again, is to try to reduce the correlation in successive messages that are passed. Each check node, on the other hand, sends a message, again, extrinsic to each variable node it's connected to, removing the information that it received on the previous iteration from that variable node. Very similar concept, if you've studied turbo codes at all, to the way in iterations between turbo codes, the way information received in by a particular decoder in the previous iteration is removed in passing its message back to the other decoder. So we compute the a posteriori probability for each code bit given the received data, and given that we know that the parity checks have to be satisfied. Okay, the messages passed to the parity checks are going to be a set of LLRs, but their signs indicate what the current estimate is of those bits, and those bits should satisfy those constraints, just like in our bit flipping algorithm. So we're going to make hard decisions once we get APP value at the end of a given iteration. We form these APP values, which are just log likelihood ratios, on each code word bit, and we get the hard decisions from the signs, and then we're going to check if VH transpose is equal to 0 or not. If it is, we'll stop, just like we did with the bit flipping algorithm, except the bit flipping algorithm we had hard decisions to start with. Here we have soft values, and we get hard decisions from them, from their signs. Or if we never get to this and we hit Imax, then we stop also. Otherwise, if this isn't satisfied and we're not at Rmax yet, we go back and just repeat. So the basic messages that are passed from a variable node to a check node. So this would be a variable. This is a variable node, and these are, say, 3 check nodes that it's connected to. So the probability Pij that we now this is speaking of these as if they were probabilities before we would form the log likelihood ratios. The probability that Vi has a certain value, given the observed value Ri, and all the messages that Vi got from the check nodes that it's connected to in the previous round, other than the message that came back from the check. So we want to send a message from variable node I to check node J. In forming the message that we're going to send, we ignore the message that came from check node J on the last iteration. That's this, in order to get our extrinsic information that we pass in our messages. And the same thing in passing messages from check nodes back to variable nodes, which we'll denote by Q. This probability, this is going to be, maybe I didn't say this precisely, this message that we pass from variable node to check node is the probability that this bit takes on a certain value, either 1 or 0, given this information. Here, the message that we send from the check node back to variable nodes is also the probability that that variable node that we're sending a message to has a certain value, either 1 or 0. Given all the other messages that we received here from variable nodes on the last round, other than the message coming from the variable node that we're currently passing a message to. So the check node in some sense has a little bit less information than the variable node in forming their messages. The check node messages are formed just only on what it got from the variable nodes the last round. The variable node messages are formed on what it got from the check nodes in the last round, plus the variable nodes always have access to what was received off the channel, and that stays there, and they use that at each iteration. So the way that the kind of flow works here is if you're sending a message from variable node 0 to check node 0, that it's denoted P00, and the information that you use is the R0, the received symbol, and these two messages that you receive from these two check nodes, the last iteration, not the one that you received from this check node. And then if you're sending a message to check node 1, you use the messages from these two check nodes, not this one. And if you're sending a message to check node 2, use these two messages from the previous round, but not this one. So that's kind of the way it goes with passing messages from variable nodes to check nodes. Passing messages from check nodes to variable nodes, and the notation here is Q, from variable node 0 to check node 0, uses the messages that were passed from the other three variable nodes connected to this check node at the last iteration. And again, if you're passing a message to variable node 1, you use these three, etc. So this is just kind of to get in your mind the idea of what this extrinsic information means and what particularly is excluded in each iteration. Or in each message, as you form each message, there's always one message from the previous round that's excluded in order to reduce this correlation. Now, if the extrinsic information from a parity check sent back to a variable node is independent of the a priori probability that that variable node started out with in the first iteration, only until it gets back via a cycle. So if you have a cycle of length 4, after 2 iterations, you won't get totally independent messages, information back to a variable node. If your cycle is of length, if your girth is 6, you get totally independent information for 3 iterations, etc. So the cycles cause a buildup in correlation. Now, I said BP decoding is suboptimum. Well, it is map under one condition, if there's no cycles. And then you can show that this is actually an optimum decoding algorithm. If there's no cycles, if you never bring back information that you previously knew. Otherwise, it's suboptimal. But there can only be no cycles in infinite-sized graphs. So in practice, this is always a suboptimal algorithm. So what about the details of the algorithm? So we initialize it the following. let's say this is the set of observed values. Now, we really, okay. We should have used R here, I think. Didn't we use R back here? I don't want, yeah. Now we kind of switched to Y. Okay. This is one thing I didn't catch in going through these. But these are the received values. These are going to be real numbers. Okay. Plus or minus. Oh, I remember now what I was going to remember. What I forgot to say. It's important when talking about the when we're talking about the binary symmetric channel, we're always talking about ones and zeros. But when we talk about the Gaussian channel, there's always a mapping that takes place at the transmitter, at the encoder. A binary 1 is represented as a -1 value to transmit, and a binary 0 is represented as a +1 value. That mapping is arbitrary, but that's normally the way it's done. So what you're really, think of your code sequence as being a sequence of +1s and -1s now. And your LLRs have plus or minus signs and magnitudes. So if it's a plus sign, it means that a plus 1 is more likely than a -1, and the magnitude indicates how much more likely it is. And the same thing for -1. So it just, even though we continue to write 1 and 0, we are, in terms of what's actually transmitted, it's +1 or -1. It's BPSK modulation with either a 0 or a 180-degree phase, which means the amplitude's either +1 or -1. So the ratio here, okay, the notation's not wrong. The R sub i's are the log likelihood ratios. The Y sub i's are the actual observed values. Okay. Now the probability, although this, okay, this would be, for the binary symmetric channel, the Y's are 0 and 1. This is for the binary symmetric channel. So if y is a 1, we get the log of the ratio, the probability, remember the log likelihood ratio was the probability the bit is a 0 divided by the probability it's a 1. So if y is a 1, the original bit being 0 would be probability p. It would have had to been a crossover on the channel. So p is the channel error probability here for a binary symmetric channel. If y is a 1, then the transmitted bit was a 1 with probability 1 minus p. So this would be the log likelihood ratio. This would be the log likelihood ratio if y was a 0. So this is the way you initialize the algorithm if you're working on a binary symmetric channel. Notice that this is a hard decision channel, but it's still a soft decoding algorithm, because we're forming log likelihood ratios here, which are soft values which depend on the channel crossover probability, and those will change as you go through iterations. The more common way we'll deal with this is the binary input additive white Gaussian noise channel. And in this case, these are real numbers. And this is the log likelihood ratio that you start out with as your initial LLR assigned to a particular variable node. Now, it didn't derive this. So you say, well, this is signal-to-noise ratio on the channel. This is what's received on the channel. So this is a point which I should make. In order for this algorithm to work properly, you need to know the channel signal-to-noise ratio. I don't know whether Adrish remembered to point that out or not. I didn't remember when I was discussing the Viterbi algorithm. For the Viterbi algorithm, you don't have to know the signal-to-noise ratio. It finds the maximum likelihood path regardless. The BCGR algorithm, you have to know the signal-to-noise ratio. It's required in the computations. Same thing here. Okay. Now, where does this, you may say, well, where does that come from? Okay, you're forming the log of a ratio of probability that a bit is equal to 0 divided by the probability it's equal to 1. Well, the Gaussian channel, remember, has the probability density functions look like this for Gaussian noise, okay? And when you try to determine the probability that an error is made, like in the little picture we had on the board the other day, you're integrating a tail of the Gaussian density function, okay? And that gives you and the Gaussian density function has is expressed in terms of an exponential, okay? And then you're taking, and the exponent is signal-to-noise ratio, okay? Then you're taking the log of that. So you get the log of an exponential term, which has a signal-to-noise ratio and its exponent. That's why you get, I'm not going through the details, but that's where that comes from when you have a Gaussian channel. So how about computing messages from the check node from a check node to a variable node? So this is kind of the initialization step. Then the next thing is how we compute messages. So this message would be the log likelihood ratio of the probability that the variable node v sub I causes the constraint f sub j to be satisfied. Otherwise, you're passing a message from a constraint node, from a check node to a variable node, and this is the log likelihood ratio of the probability that a particular value of v sub I would cause. The check is either satisfied or not satisfied at a particular time, depending on the signs of the LLRs. So this would be the probability that a particular value of the variable node causes it to be satisfied. Now that probability can be expressed in this fashion. This is the so-called we call this probability that we're sending, this is an extrinsic value. It can be represented like this, where this probability is an internal value. That's the probability that bit I primed, which is connected, one of the bits connected to this check, is a 1. Otherwise, it's the probability that that I primed has an LLR associated with it with a positive value. Or actually it would be a negative value because 1 is mapped into -1. Okay, and notice that the product here is over all the bit nodes, variable nodes, except the one that you're passing the message back to. So there's one missing here, the ith one, the variable node that you're passing the message back to, the ith variable node, is not included in this product. That's the extrinsic information. I mean, that's what makes this extrinsic. Now, where does this come from? This comes from a lemma that Gallagher had in his original work, which it really is just saying that you have a sequence of m independent random variables, and the product that set of binary random variables, the probability that set of random variables has even parity is just given by this, okay, where the p's are the probability that a particular random variable is equal to 1. Okay, and the probability that it has odd parity is given by essentially the same expression except a minus sign instead of a plus sign. So again, this is, you get a set of random variables. What's the probability that they have even or odd parity? If you know the probability that each bit is equal to a 1. Okay, and you can derive these formulas. I'm not going to prove it, but you basically do it by induction. You start with m equal 1, and then you say if it's true for m equal 1, you can easily show that it's true for m plus 1, or m equal 2. So if it's true for m, you can show that it's true for m plus 1. All right, then and again, this is where it gets a little difficult. This is the the extrinsic information in the probability domain that we're going to send back from a check node to a variable node. To get that in the log domain, we need to do this. Okay, it's log of 1 minus p divided by p. This is just the probability, the log of the probability that that variable is 0 divided by the probability that it's 1. Because p plus 1 minus p must always add up to 1. But this probability based on this lemma it's 1 minus this. So it's going to be 1 minus this thing, which is going to give us a half but a minus sign there. Okay, and also the probability, it excludes the message that came from variable node I at the last iteration. So again, the product here is not across all the variable nodes connected to this check node. It excludes the one that we're sending the message back to. So we get this then is the way we can express. Pardon? Oh, you may be struggling with the handwriting here. I'm sorry. Let me explain it first, and then I'll leave it up here for a second, because I need to go back and forth to explain it. The probability on the bottom just comes directly from this. This is the probability that has odd parity, so that it would be equal to a 1. And the only difference is, again, to make sure that it's extrinsic, the variable node that you're connected to here, that you're sending a message to, you don't want to take the message from that variable node at the previous round. So again, that's why the I prime does not equal to I. Yeah, let me finish this page, and then I'll go back and I'll point out some things you may not be able to read. Now, although I'm not going to, it seems like, okay, this looks complicated. It seems like in this procedure that we're actually making things more complicated. And we are, in fact. But in the end, we get something less complicated. So there's a relationship between a log likelihood ratio, the hyperbolic tangent of a log likelihood ratio can be expressed in this fashion. So p here is just some probability. It's not intended to be whatever we used p for. It's not a binary symmetric channel crossover probability or anything like that. It's just some probability. And this is a relationship which we can use to get these 1 minus 2 p's and put them in this form. Okay. And the Pij, these things, notice that the hyperbolic tangent here has a term log of 1 minus p over p. So the pi prime j here, instead of writing log of 1 minus the p intrinsic divided by p intrinsic, we just let pi prime j be the log of 1 minus p intrinsic divided by p intrinsic. So it's just notation. Now, not satisfied with making it more complicated, we're going to make it even more complicated. So you can then, and I'm not going to try to show this, there's a relationship between, well, maybe it's obvious, I don't know. Relationship between an arc hyperbolic tangent and this function. Now, this is not a log likelihood ratio. It's not log of 1 minus p divided by p. It's log of 1 plus p divided by p, divided by 1 minus p. P, again, here is just some generic probability. But so that's what we have here. We have the log of 1 plus something divided by 1 minus something. We can write that as twice the arc hyperbolic tangent of the something. Okay, this doesn't have to be a probability. This is just some number. Okay, so we wind up with a thing in this form. Let me actually complete this. I think it's completed on the next. Oh, that's okay. That's done, I guess. Okay. Now let's go back and look at what we've got here. Did everybody get this? This is INT for intrinsic. as opposed to extrinsic, which this is. Okay. This is just B sub j, which is just the set of variable nodes connected to the jth check. Okay, it's just a set. Okay, now what does this check have? It has messages from all the other variable nodes that are connected to the jth check node. We're not going to count VI because we're sending the message back to them. So those messages all have signs associated with them, which is either plus or minus, which means a bit is either a 0 or a 1. Okay? So that check node is sitting there with, it's getting, so it gets J is the, if it's a regular code, J is the number of edges connecting a variable, oh no, K is the number of edges connecting a check node to, it connects to K variable nodes. So there's K minus 1 variable nodes with LLRs that have come into this check node. They all have signs. Okay, and that means that we have, the current estimate is that we have estimates of whether those corresponding bits at the variable nodes are 1s or 0s. We check those estimates have a certain parity. We add them up. How many 0s, how many 1s? What's the parity? And then this is then the probability that if the other bit that's connected to this check node is a 1, what's the probability that the parity then is satisfied at this check node? So that's the probability we're computing here. Okay, and that's just the probability that the it depends on the signs of those LLRs that came from the other K minus 1 variable nodes. And those LLRs are what this intrinsic information is. But it's just their signs which determines whether or not the parity is satisfied, and that's what we're trying to compute here, the probability that the parity is satisfied by those signs, and we make some assumption about what the VI, we say, okay, what's the probability, if VI is a 1, what's this probability then that the parity is satisfied? If VI is a 0, we'd get 1 minus this. So that's what we're trying to compute here with the extrinsic information, is given the signs of the LLRs coming in from the other variable nodes connected to this check node, and the fact that the variable node we're sending our message to is a 1, what's the probability that all those bit estimates add up to 0, have even parity, satisfy the check? Well, I mean, as you do this, I mean, if you've gone through a cycle, then you've got dependence built up in computing these probabilities. It's not that it's not valid, it's fine, it's just that you're not going to convert. I mean, if you didn't have cycles, you'd converge to the correct code word more quickly. If you have cycles and you don't have this independence, then it takes longer to converge to the correct code word, and you may never converge to the correct code word. Okay, so I just want to make sure you've got what's written. So this subscript is K. This is just an index, okay, of a set of M variables. This is not following the notation of a particular belief propagation or something. It's just a general lemma. And then these are like the extrinsics. These are the things that we computed back there. And the subscripts here are j comma I, meaning check node j, variable node I. The extrinsic probability that we're going to send from check node j to variable node I. And this is the log likelihood ratio of that probability, which is actually what we send in the log domain. And then this is I prime not equal to I. The subscripts here are I primed. These are the intrinsic probabilities associated with the variable nodes I prime that are connected to this check node. This is hyperbolic tangent, TANH. Yeah, and again, this P here is just a generic. It's just a generic value. It doesn't have to be. It's not referring. Otherwise, when we use this over here, the P is actually this intrinsic probability. Okay. And then this is a new notation here. This little pi primed j is the log likelihood ratio of the intrinsic p, intrinsic probability. So this is a new notation, just so we don't have to write the logs in here that come from this substitution. And then down here, the A here means arc hyperbolic tangent. Okay. And again, this is just a general relationship like this one is up here. That's true, basically definition of arc hyperbolic tangent. And we can use that definition in our case. What we have here is the log of 1 plus something divided by the log of 1 minus the same thing. That's of this form. So using this relationship, the P here is this product of hyperbolic tangents. So that goes in the argument here. Otherwise, this P becomes this argument here. So we finally wind up, this is the message that we wind up sending to from a check node to a variable node. Now that's okay. I thought we go further than this in a second because that's still pretty complicated. But I guess we do the other messages first. The message from a variable node to a check node, the other direction. Well, here we have a priori LLR. So we're just trying to tell a check node what's the probability that, yeah.
QJI, the expression for QJI.
This, yeah.
The above expression shouldn't it have been log of PJI extrinsic upon 1 minus PJI extrinsic? The other way around. I mean, it should have been.
You know, I don't think so because I mean, it would be that way if we said if this was a 0. I mean, it could be either way. But we calculated the probability assuming that this was a 1.
So it's the LLR of the probability that Pi causes Fj to be satisfied, right? So it's 1 minus Pj would be not satisfied and Pj, the down will be satisfied.
Yeah.
The denominator would be satisfied, probability of being satisfied, and the numerator would be not satisfied. It should have been the other way around because that's the way we define Qj. Qj is the LLR of the probability that Pi causes Fj to be satisfied.
You know, let me think about this. You might be right. I mean, there could be just the thing was flipped. I think though that you can get either way depending on whether you say this is a 1 or a 0. If you're right, then if we said this is a 0, then what we have here would be correct anyway. Okay, so here what we're trying to do is send a message from a variable node to a check node saying, okay, what's the probability that this variable node has a certain value? Well, what do we have? We have our a priori probability, our a priori LLR, and we have all our LLRs from the check nodes that we're connected to. And we know that our current estimate of whether a variable node is a 1 or a 0 or a +1 or a -1 depends on the sign of the LLR that we have given all the information that we have. So if we just add up all the LLRs, okay, then the sign would tell us our current estimate of whether this is a 1 or a 0. And this is the way we make a final decision at the end. Okay, once we're finished iterating, if we've hit, or at the end of each iteration, we actually form our estimates based on this, check the parity to see if it's satisfied or not. Now, in order to pass a message back to the check node, though, we should not include the message that came from that check node in the first place. So the message that gets passed back to the check node is essentially the likelihood of that node, excluding the message that we just received from that check node on the previous iteration. So this is a much easier thing. The messages going from variables to checks are much easier than the messages coming from checks to variables. Yeah, yeah. I mean, you don't have to, but that's normally the way. I mean, because if it's satisfied, you just stop. I mean, you're never going to go any. I mean, you could in fact have the correct code word, keep iterating, and move off it. So you really should stop. Yeah. Now, okay, here's where we get back to the simplification. So this thing. Oh, maybe I should stop here and make sure that people have got. Yeah, these are. Can we read these? Yeah, I guess these are okay. This is J primed I. J prime not equal to J. Yeah. Yeah. Now here, okay, we have, we go back, we had products of hyperbolic tangents in here. Now again, I'm not going to go through the whole derivation. I was trying to do this last night and I couldn't even remember how to do it myself, but it's, you can use something called the phi function. Well, the thing you want, the first thing you do, the key thing here, is to take these LLRs, okay, and write this as the sign, so that the hyperbolic tangent of minus x is equal to minus the hyperbolic tangent of x. So you can write this as a sine times its magnitude, okay, and then you can extract the sign out in front. And so because of the product here, you get a product of signs. And that's this simplification. And then what you're left with is a hyperbolic tangents of magnitudes of these LLRs, just the magnitudes, not the signs. And those can be written in terms of this phi function, which is the log of a hyperbolic tangent. And you wind up getting, because you had a product of hyperbolic tangents, the log of a product is the sum of the logs. So you wind up getting a sum of the phi functions. Let's see, is that the easiest way? Yeah, okay. But that's fine. Whose argument is the magnitude of these LLRs. And this phi function can also be written this way. And so why bother with this? Is this really, I mean, this is, why this form rather than the hyperbolic tangent form or arc hyperbolic tangent? The phi function has an interesting property that it's its own inverse. Okay, so that allows us to, you can implement it with a table lookup, and it simplifies. You can implement this phi function with the table lookup. Actually, the fact that it has its own inverse isn't the point here. You can write this in terms of the phi function. The point here is more that you've got you've replaced these multiplications, okay, because the phi function is defined as a log with summations, the log of a product giving you the sum of the logs. So you've got in here, the difficult part of the computation now is summations rather than multiplications. All the multiplication you have to do is with the signs out here, which is just computing the parity. So that does simplify the calculation, and you can use a table lookup, which makes it slightly suboptimum depending on how big a table you want to use, to give you, just look up values of the phi function for different values of x. And x in this case is just an LLR magnitude. It's only going to be positive, okay? And so you'd have, all the positive values would be represented in this table, and you can implement it that way. Now the other thing is that you can, because this phi function, okay, the form of the phi function is interesting, and I'll just draw it on the board here. So if this is x, this is phi of x. And you can kind of see it, I mean, if you just mentally look at e to the x plus 1 over e to the x minus 1. But it looks like this. Okay, it only takes on positive values because it's a log. And its arguments are only positive values because we took those magnitudes. And we extracted out the signs. The interesting thing about it is that we've got here a sum of phi functions. And if we want to make an approximation, we could say, all right, let's say that the biggest term in this sum is kind of dominant, and drop all the other ones. Okay, well, the biggest term in this sum is going to, because of the form of this thing, is going to be the smallest value of the argument. So the smallest value of this LLR is going to dominate this sum. And we could replace this sum simply with the phi function of the minimum. We could take only the one term here instead of whatever it would be, k minus 1 terms. We could take only the one term. And then we have phi of the minimum LLR magnitude. But there we would have phi of something. And because it's its own inverse, we just get what's left is the minimum magnitude of an LLR. So we still have, this is so-called min-sum algorithm. It's an approximation to the sum product algorithm. We do the sign computation, and the rest of the message is simply the minimum magnitude of an LLR. So this is a message passed from check node J to variable node I. And we take a look at all the variable nodes connected to check node A other than variable node I. We look at their signs from their LLRs, and we compute this. And whichever one has the smallest magnitude, we just put it there. And that's the message that we send back. So this is now the table lookup isn't so bad. Of course, the table lookup, you can do a table lookup for the phi function, and depending on how big you make the table, it can be as accurate or not so accurate. This is a further simplification of the table lookup and easier to implement. Okay, let's see, did we make sure everybody's got, these again are the pi prime subscripts, I prime j. This SGN, that's just sign, okay. Again, these are the pi prime j's. Okay, I guess. Any question on that? This check node to variable node message is a difficult derivation and everything, but I'll check on that one question. You had? If there's two that are the same, you can pick either one, right? It doesn't matter. It's only the value that matters, not which variable node it comes from. Well, yeah, oh, I see what you're saying. Yeah, right. Yeah, I mean, if two of them are the same, you kind of know you're in trouble, and you may want to. I mean, there are all kinds of variations of the min-sum algorithm. There's offset min-sum algorithm. Kind of compensates for that type of situation. Yeah. And there's a couple of others. Okay, well let's try. We've only 10 minutes left. This is one of the ones I don't think I'm going to make in an hour. But let's see if we can get this. I think the rest of it will go fairly quickly. Get the general idea. The one thing there is it is complex, but when you wind up at the final thing, particularly if you do the min-sum, it's not hard to visualize. So the BEC is simpler to analyze than the. Okay, why are we going to look at the BEC? Well, it's just simpler than the BSC or the Gaussian noise channel. And we'll try to see how this works on the binary erasure channel. For the BEC, all of this boils down to two simple rules. At a check node, the outgoing message, it's going to be either one of the messages are always one of these three possible received values. It's going to be an erasure if any of the incoming messages are erasures. Okay, again, not including the one that came from the variable node that we're passing our message to. If none of those are erasures, if they're all hard values, then the message going out is the mod 2 sum of these incoming messages. Okay, to maintain the parity. Okay, you got even parity here. If you put a 1 here, you destroy the parity. At a variable node, you've got, in addition to the messages from the check node, you've got what came in from the channel. And the outgoing message is an erasure if all of the incoming messages are erasures. Otherwise, if even just one of these messages is a hard value, you take that hard value. Okay? Because in an erasure channel, once something is telling you that that's the right, you can't make errors in an erasure channel. So if you get somebody that's telling you this is a 1, it's got to be a 1 because it could not have been received as a 0. The erasures must have been resolved. And you can see, if you think about it a little bit, that it's not possible that these things are going to disagree. They'll all have to agree. And that's the value that you send. So let's just do one of these little examples again. Let's say that this is transmitted code word, and we receive, there's no possibility of error, but we receive 3 erasures. Okay? And we do a bit to check. So we have a 0 here, and it's passed to the 2 check nodes. We have a 0 here, it's passed to these 2 check nodes. A 1 goes to these 2. This is similar to the bit flipping algorithm, but now it's basically belief propagation, not just bit flipping. The erasure goes here and here, and here and here, and here and here. Okay. Now we've received messages down here at each check node, 3 messages from corresponding variable nodes. Okay, so now we want to start sending messages back. All right, well, I've got these 3 messages. I want to send a message back here. Okay. I look at the other 2 messages that I got. Okay, actually I should be looking down here. I don't want to look at this message because that came from the bit node that I'm sending the message to. I want to look at these 2. If either of them is an erasure, I'll send back an erasure, which is what I do. In sending the message back here, I want to look at not this one, but the other 2. If either of those are an erasure, and they are, I'll send back an erasure. For the message going back here, so these little symbols represent the messages going back to the variable nodes. I don't want to look at the erasure which came in from here. I look at these two, and they both agree. Okay. So I add them up, and I send 0. Okay, now I do the same thing here. Again, I exclude this one. I've got an erasure, so I should send an erasure. For the middle one, I exclude this guy. I still have an erasure. I send an erasure. Here, I exclude this guy. I've got a 0 or 1. I have to send their mod 2 value a 1, which would satisfy the parity, at least based on the two messages that I got from these two variable nodes. Then I move over here, same thing. I exclude this one. I get 2 erasures, gives me an erasure. Exclude this one, still have an erasure. Exclude this one, still have an erasure. And finally, I exclude this one. I have 2 erasures. I exclude the middle one. I still have an erasure. And I exclude the last one. I still have an erasure. So I get all of these messages have been received back at the variable nodes then from the check nodes. Now I want to look at them. And I look at what we know about this node now. Well, in the beginning we had a 0, so this is still going to be estimated as a 0. I mean, it could not be a 1. Same thing for this one, same thing to this one. The ones that have to be resolved are these. Well, now one of the messages coming from the other from the connecting check node said that this was a 0, so it must be a 0. And here, one of the messages coming from a connected check node said that this must be a 1, so this must be a 1. We've resolved 2 of the erasures. Over here, though, both of the messages coming from check nodes said that we still weren't sure. So we still have an erasure. We have to do another iteration. So we go to our second iteration. Again, we pass the zeros. We pass zeros, we pass 1s, we pass zeros, we pass 1s, and we pass our 2 erasures. And we get these messages at our check nodes. Now we want to go back. I mean, everything is 0 here, so that when we eliminate any one of these, the mod 2 sum is still going to be 0. We're going to send zeros back there. These, when we eliminate this, we have 1 plus 1 or 0, so 0 goes back here. When we eliminate either this one or this one, we get 0 plus 1, so 1s go back along these edges. Here, when we eliminate this one to send something along this edge, we still have an erasure. And when we eliminate this one, we still have an erasure. But when we eliminate this one, we have 0 plus 1, which means we want to send a 1 to maintain the parity up here. And the last one, again, since we have an erasure here, we're still going to send an erasure as these 2 messages. But up to here, we eliminate this. We have 0 plus 1. We need a 1 to maintain parity, so we send a 1. So now we've gone through the second iteration for passing messages back to variable nodes. And now we want to do the bit processing again. Look at the overall LLRs. I mean, the LLRs of all the inputs to each particular node, what their signs are. And in this case, again, that doesn't change, that doesn't change, that doesn't change, that doesn't change. But with this last one, which is an erasure, we now obtain 2 opinions that it should be a 1. Okay? So we change it to a 1. And that completes the decoding. And that completes the lecture. Okay. So, good. Although I realized going through the check node to variable node messaging gets complicated, and there were steps that I didn't derive everything. But I mean, so for the Gaussian channel, this gets to be a little complicated. For the erasure channel, it's very simple. You can kind of see how it works. But for the Gaussian channel, you just have to keep track of these LLRs, which are based on logs of probabilities, which you compute in the message passing process. How unstable is it?
How sensitive is this to value of EVY and not if we do not know the accurate value?
It's a good question. Yeah, okay. If you misestimate the signal-to-noise ratio, then the performance is worse. I mean, there are papers that have been written on that, also for turbo codes, same thing, as to what happens if your accuracy isn't as much. If you do the min-sum algorithm, you don't lose anything. The min-sum algorithm doesn't require you to know the signal-to-noise ratio, because I think we should be able to see that here. Yeah, so that's a good question. It requires the magnitudes of the LLRs. Okay, I don't think it's going to be obvious looking at this, but it is true. I mean, because just to form the a prioris to start out with, you need the signal-to-noise ratio. But it's buried in there someplace that the min-sum, if you look at it and you misestimate the signal-to-noise ratio, I believe, if my memory is serving me right, it's been a while since I've thought about this, that you don't lose anything for the min-sum, but you do lose something for the sum product. Okay, so it's how much, I mean, there have been papers written on it. I'm not sure, in general, I think the algorithm still works pretty well if you have a reasonable estimate of the SNR. But if you're too far out, you're too far off, it will not perform well, obviously. Okay.